In this video, I'm going to go over the concept of derivatives. Now, this is just going to be a basic introduction conceptually, which will go over what derivatives are, how the concept of them is derived, and as well as how to evaluate them using the basic definitions. I'm probably not going to go over the shortcuts such as power rule, all that in this video. That'll be for a later video in the same calculus playlist. So let's begin. Now, before we look at derivatives, let's look at something pretty similar. That's rates of change. Now, say you want to find the rate of change of some function, and let's call that function f of x. We know that the rate of change is the change in y. So let's write that out, shall we? So change in y over the change in x. Now, what's another term for y? F of x. F of x is equal to y in the function definition. So we can change this definition to the change in f of x over the change in x. So now we've established that to find the rate of change, you would need to calculate the change in f of x or y between 2 points over the change in x between 2 points. Now, writing that algebraically, that gives us a neat little equation. And that equation is f of, let's say, point A, which will be our first point, minus f of point B, which will be our second point, all over A minus B. Now we can use this as our baseline formula to find any rate of change of a function. To demonstrate that, let me give you an example. So let's create a nice little xy plane over here. Okay, that works. And let's take a function in red, and let's call that function f of x. So if you take this function and we call that f of x, and let's also label 2 points on that function, point A and point B in green. So let's make point A about right here on the y-axis, and then let's make point B right here. So that'll be point B, and that'll be point A. Perfect. So to find the average rate of change between those 2 points, you can think of it as drawing a line between those 2 points and finding the slope of that line. So again, let's use our formula that we have here. And that'll be, in this case, let's make point B our first point. That'll be f of B minus f of A over B minus A. Great. Now, that's all well and good, but that doesn't really represent the average rate of change of the function as a whole, because this line doesn't really correspond to this polynomial because it's linear and the polynomial is a curve. To make that better, let's make those points closer. So instead of point B being over here, let's make this point B. That's a wacky line, but as you can see, it's steeper and a bit more representative of what we have here. Now let's make point B even closer. Let's make it the bottom of this little valley right here. Let's make that point B. And as you can see, we get closer and closer to a rate of change that is consistent with the polynomial. So if we make the distance between A and B smaller and smaller, we get a more accurate slope. So let's call that distance delta x, or the change in x between A and B. And that way we can rewrite B into A plus delta x, because B is delta x units or whatever away from A. With that in mind, let's rewrite this slope formula. So f of b, now we know that b is a plus delta x, according to our new definition, minus f of a all over b again. We know that b is a plus delta x, minus a. A minus a cancels out to be 0, which leaves us with a new equation for the rate of change. And that will be f of a plus delta x minus f of a all over the quantity delta x, since a minus a cancel out right here. Now, another thing we've established is that as this distance between a and b gets smaller and smaller, we get a more accurate representation of what the rate of change of this function is. So if we make this distance smaller and smaller and smaller, infinitely smaller, but never to the point of reaching 0, because then you can't take the rate of change because you need two individual points. And we can express that using a limit. So we can say that the limit as delta x approaches 0 of, let's take our rate function that we found out, a plus delta x minus f of a all over delta x. Now, as delta x keeps getting smaller and smaller, so instead of b being at the bottom of that curve, let's say b becomes this, and then this, and then this, and then this, until eventually it's infinitely close to the point A. And in that case, you would have 2 points that are infinitely close to each other, and with that, you can determine what's called the instantaneous rate of change of a function, or in other terms, the derivative. So all a derivative really is the instantaneous rate of change of any given function. Instantaneous rate of change. That is the same thing as a derivative. You make the 2 points smaller and smaller and smaller and smaller until the distance between them is nearly zero to find what the slope or the rate of change of that function would be at a singular point. And that gives you your derivative. Now, this equation that we derived here is what's called the limit definition of a derivative. It'll come in really handy to evaluate derivatives and also to understand them conceptually. Let's go through some problems where we use the limit definition of a derivative to find out the derivative of any function and evaluate it at any point. So let's have our baseline formula up here that we can use in our calculations, and let's get started. So the function we have here is f of x equals x squared, and plugging that into our limit function, we get the limit as delta x equals 0. Now remember that f of x is x squared, so we're basically plugging in a plus delta x into x squared. So that would be the quantity a plus delta x squared minus f of x, which is again x squared, all over delta x. Yes, delta x. Um, oh, sorry, let's make this x. This is in terms of a, and this would be in terms of x. So let's just make this x instead of a. So x instead of a. There we go. And let's evaluate the square term up top. So that would give us the limit as delta x approaches 0 of x squared plus delta x squared plus 2 delta x minus x squared all over delta x. So x squared and negative x squared cancel out, leaving us with the limit delta x approaches 0 of delta x squared plus 2 delta x all over delta x. A lot of delta x's there. And let's factor out a delta x from the top. So the limit as delta x times delta x plus 2x all over another delta x. So these two delta x's cancel out, leaving us with a pretty simple equation for our final limit. So the limit delta x approaches 0 of delta x plus 2x. Now we can begin evaluating the limit. So let's rewrite the final equation we get by simplifying. And let's use substitution to solve. We plug in 0 to delta x, giving us 0 plus 2x, with 2x as our final answer. And now we can conclude that the derivative of x squared is 2x. And there are two forms of notation for writing this. Since we know that f of x equals x squared, we can say that f prime of x, signified by that apostrophe up top, equals 2x, or we can say dy, d means delta, and delta means change. So basically the change in y over dx, the change in x, equals 2x for that function. And what this 2x means is at any given x value, if you plug it into the derivative, you'll get the slope at that given point. So let's take a look. So let's say f of, let's find f of 1, f of 2, and f prime of 1, and f prime of 2. So f of 1 is x squared, 1 squared is 1, f of 2 is 2 squared is 4. Now let's look at the derivative. We know the derivative is 2x. F of 1 is 2 times, f prime of 1, sorry, is 2 times 1 is 2. F prime of 2 is 2 times 2, which is 4. So what this statement is saying is that at x equals 1, the slope of the parabola x squared is 2. And at x equals 2, the slope of the parabola x squared is 4. And that's how you can use the limit definition of a function to, the limit definition of a derivative to evaluate derivatives at any given point and find the derivative of any function that you can think of.